Okay, what's up everybody? Welcome back. Today we're talking about section 5e, which is all about commuting operators. So, first off, what does it mean to commute? Hopefully we already know, but if you don't, let's review quickly. We'll say that two operators, s and t, on the same vector space, that says, i.e., s and t are both maps from v to itself. We'll say that they commute if st is equal to ts. Similarly, same thing for matrices. Two matrices A and B commute if AB is equal to BA. All right, cool. So, why would we care about commuting operators? Well, for one, it's nice when multiplication is the same in either order. It's great when matrices, operators, what have you, behave a little bit more like scalars, elements of a field, than they do like something else. Another reason is that lots of nice things are preserved for commuting operators. That is, if two operators commute, then a number of different things you can do with both of those operators end up preserving this property or being the same. So let's do a basic example. Let's suppose that s and t are two commuting operators on a vector space V, and v1 through vn is a basis of V. Then s and t commute, like we're supposing, if and only if, their matrices commute with respect to that same basis. Let's show this. So, s and t commute? Well, that is just a fancy way of saying st is equal to ts. Naturally, if st is equal to ts, then the matrix of st is equal to the matrix of ts. But we have previously shown that the matrix of a product is the product of the matrices. So this is the matrix of S times the matrix of T, and that's equal to the matrix of T times the matrix of S. Here I'm not writing these V1 through Vn's. I'm leaving that implicit. It's stated in the statement of the theorem just to make it clear that we're not saying that they commute with respect to some choice of bases for each, perhaps different, but instead that if you pick any basis and take the matrix, it commutes, these matrices commute with respect to that choice of basis, no matter what it is. Okay, so MSMT and MTMS, these guys are equal. All right, and that's just a fancy way of saying that the matrix of S and the matrix of T commute. So we're done. S and T commute if and only if the matrix of S and the matrix of T commute. Nice. Here's another thing. So just kind of keeping the theme, which we're going to do at first here, and we're going to go through some of this early part kind of quick because it's not too hard. We're just going to show that a bunch of nice things happen for pairs of commuting operators. So here we've got S and T, operators on a vector space that commute, and lambda sorry, holding back a cough right there, and lambda an element of the field. What we're going to claim is that the eigenspace associated to lambda of S is invariant under T. Correspondingly, since we should be able to just swap out a pair of commuting operators, we'll be able to say that the eigenspace of lambda with respect to T is invariant under S as well. So let's prove this. So what we have to do here is show that we want to show that V in E lambda S implies TV in E lambda S. That is, that if you take something, that W here looks like a V. It looks like I said I want to show. We want to say that if we start with an element of the eigenspace associated to lambda for S, then we map it through T, we get back something in that same eigenspace. Okay, so to do this, suppose that V is an element of E lambda S. Then what we'll get is ST V. Well, this is ST of V, which is just TS of V, since S and T commute. TS is equal to ST, right? Okay, but this is T S of V, just to be clear, using some parentheses. Maybe I don't need to really write this step, but just to be super clear. Okay, but SV, well, this is just T of lambda V, which is just lambda of TV, which is, now notice, going to be in E lambda S. I've written that kind of silly right there. I forgot my comma. There we go. All right, not too bad. So we started out with some V in E lambda S. We mapped it through ST. We were able to flop things around. And this got us a lambda of TV. That is, we took S of TV and we got lambda of TV. That is, we got a scalar multiple of the thing we plugged in, and that scalar was lambda. I.e., if you want to say it this way, so S minus lambda I of TV is equal to 0, and TV is in E lambda S. We're done. Okay, cool. Hopefully that makes it clear. So, notice E lambda T is also invariant under S. Just swap S and T in this proof. Okay, pretty cool. So, we've shown that if you have a pair of commuting operators, that is S and T, such that ST is equal to TS, then their matrices commute with respect to any choice of basis, and their eigenspaces are invariant under each other. Nice. What else can we show? Let's keep it going. Okay, up next, we're going to tie things back into our discussion of diagonalizability in the last section and show that two diagonalizable operators can be diagonalized by the same basis if and only if they both commute. So, two diagonalizable operators on the same vector space, of course, have diagonal matrices with respect to the same basis if and only if they commute. So, let's do the proof. All right, remember, we're starting out with operators that we know are diagonalizable, and we're just trying to show that they can be diagonalized at the same time. We're not trying to show that that they can be made diagonal by some basis. We just know that they are diagonalizable already, and we're trying to show that there is some particular basis that makes them both diagonal at the same time. It may be, at first glance, it may be the case. You may think it might be the case that they're diagonalizable, but just not by any of the same bases. That is, all of the bases that diagonalize one don't diagonalize the other. And that can happen, but only when the operators don't commute. So, let's go in one direction. So, let's say, hey, let's suppose that S and T are operators on V, and let's suppose that these both have diagonal matrices with respect to a basis V1 through Vn of V. Okay. Then Ms times Mt, well, this is just, let's write it as like lambda 1 through lambda n, zeros everywhere else, and then you've got some, let's call it eta 1 through eta n, zeros everywhere else. This is just going to be lambda 1, eta 1 through lambda n, eta n, zeros everywhere else. But that's just, this is kind of going down the page a little bit here, but this is just eta 1, lambda 1 through eta n, lambda n, zeros everywhere else, since multiplication in the field commutes. And this is just mt, ms, where I'm skipping writing the step where I undo that multiplication right there. Or even if you want me to write it here, I'll do it real fast. I'll say, hey, look, this is eta 1 through eta n, zeros everywhere else, and then lambda 1 through lambda n, zeros everywhere else, and this is equal to the matrix of T times the matrix of S, and hey, wouldn't you know it, we're done. Okay, cool. Using the previous result, that says that the matrix of S and the matrix of T commute, if and only if S and T commute, we are done. Okay, kind of nice. All right, now let's go in the other direction. So, in the other direction, suppose S and T in LV are diagonalizable, commuting operators. What we want to show is that there is some basis that diagonalizes them both at the same time. So to do this, let's let lambda 1 through lambda m, so lambda, denote the distinct eigenvalues of S. Then we have, and this came from something we did last time, V is equal to the direct sum of E lambda 1S plus dot, 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 all the way down through E lambda MS. So last time we showed that if S is diagonalizable, then V, the vector space on which S is an operator, is a direct sum of the eigenspaces of S corresponding to its distinct eigenvalues. All right. Since E lambda K S is invariant under T for K in 1 through M, we get that T restricted to E lambda K S is an operator on E lambda K S, okay, and is also diagonalizable since T is. So E lambda K S has a basis of eigenvectors of T restricted to E lambda K S and hence of T. So it has a basis of eigenvectors of T. Combining bases for each, we get a basis of V that consists of eigenvectors of T and I'll say which are also eigenvectors, which are also eigenvectors of S. since they belong to an eigenspace of S. Okay, sweet. Hence, the matrices of S and T with respect to this basis are both diagonal. We proved that last time when we were talking about diagonalizable matrices, or maybe actually 2 times ago. But when we were talking about diagonalizable matrices, we said, hey, a basis diagonalizes a operator's matrix. It makes an operator's matrix diagonal. That says that the basis consists of eigenvectors of that operator and vice versa. So we found a basis that is all eigenvectors of T, and all of those eigenvectors of T are also eigenvectors of S. And accordingly, with respect to that basis, both the matrices have, or both the operators have diagonal matrices. Okay, cool. Now here's another result that just kind of follows the same sort of logic. It says that, hey, every pair of commuting operators in a finite dimensional non-zero complex vector space have a common eigenvector. So let's do a proof of this. Since this last one told us that, hey, you can find two matrices, you can find a basis that diagonalizes both of these guys. Well, all the things in that basis have to be eigenvectors of both S and T. All right. This seems to say that they share some eigenvectors, right? Okay, so let's do it. Suppose V is a non-zero complex finite dimensional vector space, and that S and T operators on V commute. Okay. Let lambda be an eigenvalue of S, which exists since V is complex and finite dimensional. Okay, we showed that before. We said, hey, when do we have eigenvalues? For sure, you have them for complex vector spaces, finite dimensional complex vector spaces, because in that case, the minimal polynomial completely factors into linear terms. That is, there's no quadratic pieces, things without roots potentially, like what happens in the reals, right? Stuff like x squared plus 1, which has no real roots. Nothing like that happens in the complex plane. So S has at least one eigenvalue. All right. So E lambda S is not trivial. After all, that's what it means for lambda to be an eigenvalue, that the null space of S minus lambda I is not trivial. So this guy is invariant under T, and therefore T restricted to E lambda S is an operator on E lambda S. Same trick as before. Okay, so T restricted to E lambda S has an eigenvalue for the same reason S does. And must therefore have an eigenvector. But this eigenvector is in E lambda S, so it is also an eigenvector of S. Hey, they have a common eigenvector. Cool. All right, let's keep it going. Let's do some more. Okay, up next, we're going to show that commuting operators on finite dimensional complex vector spaces are simultaneously upper triangularizable. Notice, before we said, hey, if you have diagonalizable operators on the same vector space that commute, then they can be diagonalized by the same basis. They're simultaneously diagonalizable. Here we're saying that commuting operators on any finite dimensional complex vector space are simultaneously upper triangularizable. We are not necessarily here claiming immediately that S and T are already upper triangularizable. It just in fact turns out that the only things on finite dimensional complex vector spaces that can commute are things that can be made upper triangular in the first place. It's kind of cool, actually. Proof. Let's do it. And in fact, notice, since you can always find something that commutes with an operator, for example, the identity map, and since the identity map is certainly upper triangularizable, this says that matrices are upper triangularizable if and only if they commute with some other operator. Oh, cool. And in fact, in the complex case, this is an alternate way to prove that all operators are upper triangularizable, which we proved before. So let's do this. We do induction. We do induction on n, which we'll take to be the dimension of V. Let's say for n equals 1, every matrix of any operator is diagonal, so we are done. Since diagonal matrices are certainly upper triangular, after all, there's nothing except a diagonal element, or an element on the diagonal. There's no non-diagonal entries in any matrix over a vector space of dimension 1. Okay, cool. Inductive step. Okay, so the inductive step, this is the base case. Inductive step. So suppose the result is true for all values less than n, which we'll say is the dimension of V. Okay, so let S and T be an LV and be commuting operators. So let S and T and LV be commuting operators. Okay, then by our previous result, so our last one, S and T have a common eigenvector. Let V1 be such an eigenvector of both S and T. Then SV is in the span of V. V1, sorry, SV1 is in the span of V1, and TV1 is in the span of V1. So, let me zoom out a tiny bit. I shouldn't have scrolled quite as far there. Okay, so what we can do now, let W be the subspace of V such that V is equal to span V1 direct sum with W. That is, just take V1, extend it to a basis of V that is treated as a list of length 1 and extend it to a basis. Then we'll just take W to be the span of the rest of the vectors in that basis. That is all the things that we added in the extension. Okay, cool. So define P in L VW by P of V, which will be equal to P of AV1 plus W, since any V in V is something in the direct sum of the span of V1 and W, so it's AV1 for some A in the field and some W in W. All right, we'll have this be equal to W. Okay, cool, nothing too crazy. All right, then we will show the following. So here's what we're going to do. So we're going to take PS and PT, which notice are now linear maps on W. Or I guess we could say that they are. If we should be a little bit careful here, I guess. I should really write this. Where here I am maybe in some small way actually abusing our abusive notation, and meaning by this restriction here, I mean that S restricted to W is in L WV and T restricted to W is in L WV. So that's slightly different than our usual restricting an operator to an invariant subspace thing, since we don't yet know that S or T have W as an invariant subspace. So I just mean the usual restriction right here. So we'll show that these two operators commute. Now to do this, here's what we'll do. So, okay, I'll start out by showing that P, S restricted to W of P, T restricted to W. So I'll do PS and PT. And I'll do this guy too, some W and W. Okay. Now, what I'll get, and this might seem a little bit weird at first, I'll get PS restricted to W, and then, putting some parentheses, when I apply T restricted to W, here, what's going to happen? Well, just think about it real quick. I will get this. Now, T, so when I apply P, all I'm doing is I'm taking out the part that lives in the span of V1, right? And I'm just getting the W back, yeah? So when I apply T here, all I'm going to do is I'll send this W to something that lives in V, and so I'll get a TW minus some A V1, since I pulled off that piece there that is not in W. So here, I'll write that momentarily. So here, down here, I'm saying where, and this is the piece that maybe is a little bit weird. What I'm trying to say here is that TW is equal to, so here I'll write it like this. So TW will be equal to some W tilde plus AV1 Okay, so you take TW, you map it to something in V, but everything in V can be written as something from the span of V1 and something from W. We'll let W tilde be this thing. And so if you want to see what P does to TW, all it does is it subtracts off that piece that is not equal to W tilde. It gets rid of it. So let's just write it as a subtraction. Okay, cool. Now when I do this, all I have to do is just write what goes on here. Okay, so now I have P applied to, well, I'm going to take S and I'm going to apply it to TW, and then I'm going to apply it to AV1. Okay, so now I will get S TW minus S A V1. But hey, this is just equal to P of STW, and I'm applying S to AV1, but V1 is an eigenvector of S. So SV1 is in the span of V1. Oh, okay. So really this is just some, I can write it as like some, I'll write it as, say, I'll call it A tilde V1. And now, when I apply P, I just get rid of that piece, right? For sure. So, I just get PSTW, for sure. Okay. But hey, wait a second. PST of W? Well, this doesn't seem so strange. Notice I started out with PS and PT, right? Okay, now I am supposing that S and T commute, so I can flip these bad boys right here. And using the same logic as before, this is P of T restricted to W, P of S restricted to W. So I've shown that P of S restricted to W times P of T restricted to W is P of T restricted to W, P of S restricted to W, applied to W. Let me make that last little W here a little bit more clear. So I'm applying this to W. Oh, okay. So P of S restricted to W and P of T restricted to W are commuting operators on W, and dim W is equal to dim V minus 1, which is just equal to N minus 1, which is strictly less than N. Oh, okay. Cool. Therefore, the inductive hypothesis applies, and both can be simultaneously upper triangularized. Oh my goodness, what a lot of writing. Okay, so both of these guys can be simultaneously upper triangularized. So, hence, taking V2 through Vn to be the basis of W, doing this, V1 through Vn, simultaneous, the upper triangularizes S and T. Why is this? Well, since, now just think about it really quick, since, write it this way, a lot of writing right there. Since SVK is in the span of V1 through VK and T of VK is in the span of V1 through VK, this is super easy to see because SV1, as we've already noticed before, is in the span of V1 and T of V1 is in the span of V1. And since V2 through Vn upper triangularizes S restricted to W combined with the projection P and T restricted to W combined with the projection P, all this says is that S of VK is in the span of V2 through VK for K greater than or equal to 2. Oh, cool. Nice. We're done. All right, maybe that was kind of a long proof, and especially the part where we had to do the projections might have felt a little bit weird. But it is kind of neat to know that simultaneous upper triangularizability, which seems like a weird thing, is a way of saying that S and T. So here it's a consequence of S and T commuting. So S and T commute implies there is a basis of T such that S and T are both upper triangularized by that basis. Put it another way, S and T not upper triangularized by any basis implies that S and T don't commute. Oh, kind of cool. Okay, neat. So let's go a little bit further and do one last theorem for today, tie a bow on chapter 5, and get ready to go into the next section. Okay, last fact of the day, and this one's pretty nice actually. I think it's got a really clean kind of proof. So, last fact. Suppose that V is a finite dimensional complex vector space, same setting we've been working in for the last couple of proofs right here. And let's suppose that S and T are commuting operators on V. Then, here's the claim. Every eigenvector of S plus, or every eigenvalue of S plus T is an eigenvalue of S plus an eigenvalue of T. And every eigenvalue of S times T is an eigenvalue of S times an eigenvalue of T. This is not normally true. That is, for non-commuting operators, this is almost never the case. Normally, you cannot determine the eigenvalues of a sum just by summing together eigenvalues, nor can you determine the eigenvalues of a product by just taking the product of eigenvalues. Generally, you have to recompute the whole business. It's kind of an annoying process. But we can do this here very easily, and in this one case, it does hold. So, let's prove this. First, note that if A and B are upper triangular, matrices, then so is A plus B and A times B. Moreover, the diagonals of A plus B and A times B are the sum, respectively, product, are the sums, respectively, products of the diagonal entries on A and B. That is, just write it like this. So, A plus B, well, just write out what A is. It's A 1, 1 all the way down through A N, N, and gonna go all across here. So I'll get A 1, 1 all the way over through A, let me make sure I got this right. It'll be 1, N, and all the way down there. And everything over here is zeros. And then our B will be B1, 1 through B1N, going all the way down. Let me put my commas. I think I forgot a comma or two right there. Between my indices Bn, comma, N. Okay, zeros everywhere else since they're upper triangular, and I'm adding them together. And what I just get back is I get A11 plus B11, forgetting my commas yet again, dot, 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 all the way down through A1, comma, N plus B1, comma, N, dot, 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 all the way down through AN, comma, N, plus BN, comma, N. And hey, it's just zeros down there. So wouldn't you know it, making that look a little bit cleaner, which is this thing is upper triangular. Similarly, if I take A and B and multiply them together, then I'm just going to take, let me select this piece right here. Oh, so much better than having to rewrite it. I don't know why I always forget to do that. And now I can just take and I can erase right there. And all I have to do this multiplication is just the usual old across and down. And so as I do this, I get A11 times B11 in the first entry. Just go across the A and down this. Everything's 0 below B11. And we just similarly go down on through. And by the last one, we're going across, and there's only one non-zero entry here, ANN. And as I go down, I just pick up that BNN. So I get ANN, and then I get my BN comma N in the last entry. And over here is just some stuff. It doesn't really matter what it is. You can write out the formula for it. It's not terrible. But just the whole point is that the things in the diagonals are the product of the diagonal entries in A and B. So, since there exists a basis of V with respect to which both S and T have upper triangular matrices, and since the entries on the diagonal of an upper triangular matrix of an operator are the eigenvalues of the operator, we are done. Oh, yeah. Wait a second. That's it. All we had to do was show that every eigenvalue of S plus T is an eigenvalue of S plus an eigenvalue of T. Well, take a basis that makes both S and T's matrices upper triangular. This means that the diagonal entries on the matrix of S are the eigenvalues of S, and the diagonal entries on the matrix of T are the eigenvalues of T. So when we take S plus T, well, the matrix of that is just the sum of the matrices of S and the matrix of T, and so the diagonal entries are just the sum of the diagonal entries of the matrix of S and the matrix of T. That is, they are sums of eigenvalues, and these are the eigenvalues of S plus T. Same thing for the product. Bada boom. Not too bad. All right. Well, that ties this up. Next time, we're going to start talking a little bit about, get ready. We're going to talk a little bit about inner product spaces. It's going to be cool. We're going to introduce some geometry. We're going to give ourselves a notion of angles. It'll be a lot of fun, and we'll be able to do a ton of cool stuff with it. So, I'll see you next time. Have a good day.